This morning we're looking at optimisation of lead-acid battery technology for use effectively in the future. If we move forward now, a couple of things there. What we're going to talk about this morning, energy storage trends. Energy storage is certainly a buzzword at the moment and is going to become critical as we move on to the future. But I think it's important to remember that energy storage is nothing new. It's been around for decades, if not centuries. Batteries have been around for decades, if not centuries. So I think what we want to do today is discuss how you could use your energy storage infrastructure, including the batteries, to perhaps meet some of the challenges that we see in the immediate future. So we're going to outline what that future, where we think the market's going, and how advanced lead-acid battery technology can begin to meet some of those requirements. In order to do that, I want to go through the advanced technology. We get very hung up on different chemistries within the energy storage sphere. You may see one chemistry as opposed to another, but even within those chemistries, there are nuances, there are differences within certain chemistries. So what I want to do is just highlight perhaps that, it's not just lead acid against other chemistry. Within the lead acid sphere, there are opportunities to use more advanced lead acid, whether it be from EnerSys or anybody else, to meet some of the requirements. And there are some advantages, certainly in the short to medium term there. There is a trend to specialization. What does this mean? It means effectively that as we go through and explore the trends that are going to happen in the market over the next few years, we're already seeing that certain applications demand certain parameters, and you can tweak the existing technology in order to meet those requirements. We can then move on away perhaps from battery chemistry to electronic monitoring of a battery. That is something that we are beginning to see more and more of. It's certainly a trend within the industry and will certainly allow you to get more, or the end user to get more out of their asset, their energy storage asset. Critically, there's going to be a key role in sustainability. Without going too much into it now, there is going to be a move from nice to have to no, you must do this, and that is going to be a critical trend over the next 5 years, particularly as the new battery directive comes into force within the EU. Then finally, we're going to wrap everything up and hopefully get into some questions. Okay, so what we'll do is move forward now. I think it's possibly worth, I have a grasp of water, taking a step back and say, right, what does energy storage actually do? As I said, batteries have been around for centuries. Before we had concerns about the environment and climate change, batteries around. What did they do at that time? So in the sphere that we're talking about today, a battery was designed to support a load when the supply fails. Now, this could be done either in a controlled way or in an uncontrolled way. What do we mean by this? An uncontrolled way is when the lights go out in an unexpected fashion. So effectively the power shuts off. And a battery was always designed to act as a safety net for any demand, for want of a better word, to keep the lights on in a hospital, or something along those lines, or to keep the phones running. So it caught the voltage and ensured that you had continuity of supply. And again, this has been around for years and years and years. You can also use batteries in a controlled way to support a load. This is something I think we're going to see more of as a trend moving forward. So, a typical example here or in the past has been, we need to do some maintenance. So we're going to go on battery load for a certain amount of time. But Obviously, what you can do now is during peak times, you can also go onto your battery or your whatever your energy storage backup is. It may be generators, for example, via a battery. Again, you could do this in a controlled way. Now, the difference is if you're doing it in a controlled way, you can choose your battery technology and size the battery to meet that requirement. Okay, so batteries are moving away from a safety net, perhaps, hopefully may never be used, particularly in a reliable grid application, to something to where we take a step back and say, actually, you know what, we're not going to use them as a safety net. We're actually going to use our asset to support the load on a wider basis. Now, that may be to support grid infrastructure, and it may be to support grid infrastructure in either there's too much power in the grid or too little power in the grid. It may be to support it at a regular time. It may be to support it only when, as happened recently, we've gone through a hot spell and everybody put their air conditioning on. So from that point of view, batteries and the existing infrastructure where batteries are being used can support the grid moving forward. Okay, so what are the other energy trends that we've identified as major battery players within the market? So clearly we've got power shortages and critically grid fluctuations. And sometimes these, as I said, can be both planned and unplanned. Sometimes we see a little bit of advance notice. For example, we know that it's going to be hot. We know that the nuclear power station may have to go offline a week next Tuesday. So from that point of view, large battery users can be incentivized to support trends within the market. Secondly, and just in general, and taking a step back, forgetting about the wider issues around grid infrastructure, in general, battery backup sizes are growing. And this is basically due to longer autonomies and higher power requirements. Higher power requirements, classic example will be data centers. Data centers are getting bigger, therefore they need a higher power requirement. Longer autonomies, this is a trend within society. So effectively, as we become more and more reliant on our infrastructure, our electrical infrastructure, the basic requirements, we are moving to the requirement to have longer autonomies. Historically, you could perhaps look at getting out at being without a mobile phone for 20 minutes to 1 hour. Now that's not acceptable because all of the critical infrastructure relies on that mobile phone infrastructure. So we're moving to longer autonomies, and longer autonomies leads to bigger and bigger batteries. Roughly speaking, if a battery needs to goes from 1 hour to 2 hours, you need a bigger battery. Thirdly, battery operating temperatures. In general, batteries are strongly affected by temperature. And I think it's important to remember this is across all chemistries. But if you look at the lead acid battery, a lead acid battery is impacted by temperature. In order to reduce operating costs while also increasing or keeping the life of the battery, you need to have a battery that perhaps will be more able to tolerate higher temperatures or lower temperatures. In the UK, we've always had quite a temperate climate. So effectively, it's been relatively easy to keep your battery operating at 20 degrees. But clearly in other countries, battery operating temperature is more of an issue, particularly in sub-Saharan South Africa, for example. And battery manufacturers have tweaked the chemistry to allow for higher operating temperatures. Moving on from that, carbon footprint is also critical. We'll move on to that in a minute, but I think it's always important to say that the battery is only part of the system. And if we want the system to reduce its overall carbon footprint, ensuring that the battery plays a role in that is going to be very important. And finally, that links into sustainability. And again, I've made the point before, and I'll make it again, and I'll make it again after this one. We are going to move into an area where reduction in carbon output is going to be critical, and is going to be legislatively forced on operators. And I think the energy storage, whatever that energy storage is, will need to play a key role in that, both from how it's produced, how it's used, and what happens at the end of the energy storage life. Okay, so battery with the cold. As I said, moving back, we said that there is lead technology, there is lithium technology, there is nickel-based technology. But within that, there are various different types of battery. So what I wanted to do today is perhaps just highlight the difference between within the lead-acid battery sphere. So lead-acid batteries are used and have been used for over 120 years. They're used in everything from automotive vehicles. Chances are they're going to still continue to be used in electric vehicles. They're used as energy and grid support. Within that, though, not all lead-acid batteries are the same. What we want to do today is just highlight that within you can have a VRLA battery. Within the VRLA battery, there are different types of product. And what EnerSys can offer is what's called the TPPL battery, which has TPPL stands for thin plate lead, thin plate pure lead rather. Now, that is an advanced lead-acid battery. It's been around for 20 years. It is used in multiple applications and can be used to meet some of the energy trends that we've already outlined. Some of the advantages: higher energy density. It is capable of being used in cyclic applications, which again goes back to the trends that we saw earlier. And based on that, faster recharge. Battery is only part of the system. If you discharge it, it is just as important to understand how you're going to recharge it. And it also has a longer shelf. So moving forward, why would you use TPPL technology? TPPL is a proven technology. You could use it within the existing infrastructure. As I said, if we're going to meet our climate goals, there are going to be a number of different ways in which we were going to do that. Clearly, large energy storage is going to be part of that. Non-chemical ways of energy storage is also going to be a part of it, whether that be anything from hydro to hydrogen. However, using the existing infrastructure is going to be a quick win. If we can tweak that, if we can use that structure with advanced batteries to meet some of the criteria, to meet some of the peak loads, then TPPL is ideally placed and is currently being used to do that. So I think it's important to remember that TPPL is there. Also, not just for EnerSys, but within the lead-acid battery industry, the lead-acid battery manufacturers are continuing to innovate, to use the technology to meet the current requirements. So it's important to remember that the future is matching the energy storage asset to the end user requirements. We see the trends going in one way, and there's no reason why we can't use lead-acid batteries from whatever manufacturer, from whatever tweaks, that whether it be TPPL or something else, to support the network. So what we're going to do now is we're going to go back to the key trends, and we're going to identify exactly how some of these batteries meet those key requirements. Number one, we mentioned about power shortages, grid fluctuations. In the UK, we're going from a very, very stable grid to perhaps something that is less stable, either through design or through the fact that we're now relying increasingly on other sources of electricity generation. So in order to do that, how can batteries play a role? Well, we talked about having a battery asset which is designed to back up your power supply or your load but perhaps historically, under normal circumstances, would never be used. Okay, let's move to a situation where we're saying, actually, we do need to use this battery. We need a base load, that's fine, but we also need the battery to be used on a daily basis. So this is technology that was basically developed for areas of unreliable grid, and almost came from the telecom sector there. And what the XC Plus is, it takes the basic battery that has a good reputation in terms of being a reliable backup and says, okay, with this product, you've tweaked it so that you can allow the battery to be cycled on a regular basis. Yes, you need to control that cycling, but it will allow you to use your battery asset in a controlled way in order to, A, primarily back up the function of whatever the battery is for, but also be used to, in a controlled way, to perhaps support the grid. So by doing that, you are taking your standard lead acid battery and perhaps moving it and tweaking it to say, right, I want this one to be cycled. And that's the XC Plus product. Secondly, we've got battery backup sizes. So as I said, they're growing in many sectors. How are we meeting this challenge? Okay, so we're moving from cycling now. So okay, we're not quite so bothered about cycling. What we want is a high rate performance. Clearly, this is driven from the data center industry, where they want more and more power in smaller and smaller spaces. And to be honest, you're going from perhaps a utility sector where you wanted the battery to support 1 hour, 2 hour, up to 24 hours in some cases. Whereas the data center industry, right, says, actually, you know what, we want 5 minutes. So from that point of view, you can take equivalent batteries and equivalent footprints and tweak it, optimize it for 5-minute high rate performance. And again, you get some of the advantages that you've had before, the basic reasons why you would use a lead acid battery, the reliability, the proven in technology, the fact it fits in with all the other infrastructure that you have available, but it's also tweaked to say, you know what, this is designed specifically for very, very high rate discharges. So it becomes a power density issue. Power density is particularly important because space is money these days, particularly in these larger UPSs. Okay. Thirdly, operating temperatures. We're beginning to get into the sustainability sphere here. So, historically, batteries were rated at, say, 10 years at 20 degrees C. As battery operators, how do you ensure that your battery remains at 20 degrees C? Specifically, you have an air conditioning unit. Air conditioning units, A, use electricity, and B, use carbon. By ensuring that you can perhaps widen the window, the operating window of the battery, you can then reduce your reliance on air conditioning. So specifically, if you can turn the air conditioning so that it only comes on at 25 or higher, you are then reducing your carbon footprint and also immediately saving electricity costs. Now, that historically was at the detriment of battery life. However, again, through a clever redesign of the battery, we are now able to offer 10 years at 30 degrees. That means that the battery is able to operate at higher temperatures, at a higher temperature window. And this has been taken on by a number of operators in the UK who are effectively turning up the air conditioning, saving money, and ensuring that the batteries still get the life that they were expecting historically. So that's just 3 examples. We've got cycle life, high rate performance, and high temperature performance, where you've taken the existing advanced lead acid product and tweaked it to meet the trends that we basically see coming in the next few years, but also are here and now. So to sum it all up, then you have your base technology based on advanced lead acid TPPL solution that is proven in the existing markets across the ranges, and we've also matched them now for high rate, high cycling, and high temperature. So again, I think one of the things that we want to just emphasize is that lead acid batteries do have a future, certainly in the short to medium term. And this can happen across the piece. Within that, we've also got other technologies. Just one off the top of my head is the Odyssey product, which is used in vehicles, whether that be large trucks, because it meets the demands of the truck manufacturers, and also for electric vehicles, where it basically sits behind the power source of the electric vehicle and ensures that in the event of something happening, the vehicle can be there. So I think lead acid batteries do have a future. Okay. Moving on to the second part, I want to discuss a little bit about battery monitoring. And again, this is almost a quick win for the end user. It is something that is available today. And we've discussed earlier about using your battery asset more. Historically, the battery was just something that sat in a building and hopefully would never get used. Now we're saying, actually, you know what, we're going to use that asset far more. In order to do that, yes, we can change the product, but we also need to ensure that the battery is used in the best way possible to optimize performance. One of the ways that you can do that is through the electronics. And clearly, other chemistries, specifically lithium, has a battery management system. Now, there's no reason why battery management and, yes, battery monitoring cannot be used with other technologies to get the most out of your asset. If you're going to use the asset, you would need monitoring to support that asset. Okay, so based on that, it's important to remember that the battery is only part of a system. If the system fails, the battery will fail. But the first thing you will know, that you'll notice that when the battery fails is when the system fails, rather, is when the battery fails. So battery monitoring can protect the end user in supporting their asset, and it is a relatively low cost investment. And I think, again, as a trend, we're seeing particularly the more savvy end users begin to embrace monitoring in order to support the asset that they have and to ensure that they're optimizing the core battery technology, whatever that core battery technology is. And we're going to see that across the piece, because other chemistries require battery management, and there's no reason why the advantages that battery management confer to those other chemistries can't be used with lead acid batteries. Okay, so why is battery monitoring important? A number of reasons. We've already mentioned you can control and monitor your asset, an asset that ultimately the end user has invested in. But also, battery conditions can change. We've mentioned earlier about high temperatures. By switching off the air conditioning or having a wider window, you effectively save money and save carbon. So battery monitoring can also support that by ensuring that the steps that are taken in order to save money, to save carbon, are the assets, including the battery, are well protected. A couple of examples. You can have site history, You can monitor, control, and limit the battery discharge. You can react to temperature changes. And yes, you can also understand when a battery might need to be changed. And again, if you go back to the sustainability piece, that might mean that you get longer life out of the battery in the end. If the conditions have been very good, perhaps the expected life was, I don't know, 8 years. Suddenly, with monitoring, you can say, I'm not going to run it for 8 years. I can run it for longer. Why is that important? As we go to a more circular economy, getting more out of your asset, basically writing off the carbon over X plus 10%, X plus 20% years is going to become more and more critical. And again, this battery monitoring is currently being used in a number of industries and is available today. So it's not something that will happen in the future. It's something that is happening now, and it's an example of how the industry is reacting to existing trends. Finally, sustainability. Sustainability is going to become increasingly important in the energy storage sector. The energy storage sector has been around for centuries. Suddenly, over the last 10 to 15 years, it's becoming front and center, shall we say. That's great. It means that we now work in a very fast-moving environment. People are being encouraged to move towards use of energy storage systems, whatever they are. But as part of that, it is clear that the legislators will also ensure that the green credentials of the energy storage sector are monitored and moved so that we are anything that we do to move batteries to front and center, it's to ensure that we really are moving towards a low carbon base. We're already beginning to see pushback in certain sectors. Are electric vehicles as clean and green as perhaps they've been sold to us? And what you can see is that the legislators and the new EU battery directive is going to enforce this, is going to ensure that the battery industry, the energy storage industry, needs to do their bit so that any questions around greenwashing, etc., are addressed. So a couple of things where this comes forward. So number one is recycling. There is going to be a very strong push towards a circular economy. As part of that, so it's not just about the carbon content associated with your energy storage solution, with the production of your battery, it is what happens at the end of its life. Now, lead-acid batteries are ideally placed for that for a couple of reasons. First of all, the recycling stream is already established. Most of the batteries, in fact, 95% of the batteries placed on the market today are currently recycled. Why? Fundamentally, it's because those batteries have a value at the end of their life. Therefore, it is very easy to set up a recycling stream. And this is going to be very, very important as we move forward. And certainly, it is going to be an advantage for this technology in the short to medium term. Absolutely, other chemistries will catch up, particularly as they more and more find their way onto the market. But at the moment, and in the short term, lead-acid batteries and TPPL as part of that have a safe, circular, and sustainable recycling stream. As I said, 95% of them are currently collected and recycled. Compliance with sustainability standards is going to be important, and it's going to go from a try to look at us, aren't we good, to no, you must comply, you will be forced to comply. And all manufacturers will publish their data with the aim of a reduction year on year on the carbon that's used. We've got an example there from EnerSys, but other battery manufacturers will do the same. And certainly there will be a push to reduce the amount of carbon associated with battery production on a year-by-year basis. This will include, for example, placing the carbon content of the battery actually on each individual block. So you may have a block that was manufactured in, say, 2024, which will have a carbon content on. The expectation is that that block in 2026 will also have a carbon content on, and the expectation is that that carbon content will be reduced. So as we not only publish the performance of the battery in terms of its voltage, in terms of its ampere hours, in terms of its watt hours, there will be a move to putting the carbon content on the battery itself. And then as a broader trend, there will also be a move to reduce that carbon content. And again, this legislation will be chemistry agnostic. It won't matter whether it's lead or whatever. They will push, the legislators will push in order to have this happen. And I think it's important to remember, particularly from an end user point of view, that this is going to happen. And again, one of the advantages of lead acid is that it has a value at the end of life. The example that we always use is that if you want a battery to be recycled, all you need to do is I'm certainly not recommending this, but you can put it on the end of the street and it will be recycled. Somebody will pick it up and recycle it because it has this value at the end of life. It has an established circular supply side, and that's going to be critical, particularly in the short and medium term. Okay. We've touched on carbon content. Just want to, as we come to the sort of the end of the presentation now, just touch on how we calculate carbon content. And this is today, and how it is likely to change moving forward. This is something I think we'll see in the next couple of years. So, number one, carbon content of a battery, and how is that associated with manufacture? So, effectively, that is the carbon, the energy used to manufacture the battery at point of manufacture. It's based on, put simply, the gas that might be used to melt the lead, but also the electricity that might be used to light the building in which the battery is manufactured. So that's effectively the carbon that's associated with the manufacture of the battery, and that is a value that we know and understand, and certainly as a battery manufacturer, we're working to reduce on a regular on a year by year basis. In addition to that, there is what's called scope 3, which is the carbon associated with the full supply chain, whatever that may be. And I think that's something that will come in the short to medium term. At the moment, it's just scope 1 and scope 2. We've outlined that there. In terms of the battery use, so in other words, the carbon that's associated with the battery while it is actually at the customer doing something, it is noticed that the battery as a backup supply doesn't use a huge amount of carbon through its life relative to the carbon associated directly with manufacture. And in fact, the carbon associated with use is probably less than the carbon associated with manufacture if the battery is never used. Now, clearly, if the battery is cycled, therefore it's being recharged on a daily basis, then suddenly that source of recharge, whether it be renewable or something else, can become critical. But at the moment, the area of focus will be on the carbon content associated with manufacture. And I think as end users, you will begin to notice that that carbon content is going to become critical. And I think end users are going to be encouraged to ensure that the products that they use are optimized so that the carbon content is reduced. Okay. we're getting to the end now. So a couple of things just to sum up and hopefully reiterate from this presentation. So number one, lead acid batteries are still widely used. Yes, other technologies are going to come in. Yes, other technologies are going to grow rapidly. Yes, those technologies are going to almost produce their own new applications. However, lead acid batteries will continue to be used and they continue to be the source of a lot of investment while meeting the requirements of society in terms of energy storage, which, as I say, will be chemistry agnostic. EnerSys are investing in lead acid batteries. I think it's worth mentioning that EnerSys are also investing in lithium batteries. So we're not trying to highlight one technology over another here, but lead acid batteries do have a future, and EnerSys is not the only company that are investing in that. With the support of by tweaking the chemistry, but also with the support of electronics, for example, the end user can make quick and easy wins to ensure that their existing infrastructure meets the requirements of society moving forward. And as part of that, because it's a long-established technology, lead acid batteries are in a good position to meet their sustainability goals today. Okay, I think that's it, Jordan. I'll hand back to you.